Yes, hello. I think we're bound down to the core rendering people here. Yes, let me quickly talk about myself. So this is joint work with the compiler department at Saarland University. Myself, my name is Philipp Slusallek. I'm a professor for computer graphics at Saarland University. I actually started off as a physicist studying physics, like our first speaker today. But I don't consider myself a physicist anymore. I kind of moved into graphics. I actually did my PhD about lighting simulation with the vision system, actually implementing Renderman and the Renderman shaders and using a Monte Carlo renderer at the time as well. That was 95. Then I moved to Stanford, was a visiting assistant professor working with Pat Hanrahan. And when I came back to Saarland University, we looked at, instead of the realistic rendering, like doing it right, we started looking at doing it really fast. And that was the start of the real-time RayTracing work at the beginning of 2000, 2001, and so on. We did a lot of work in this area, but eventually it became clear that the way we were writing these renderers was just too cumbersome. We kind of stopped doing this. We started looking for better ways to write renderers in a high-level way without going back down to the core, like essentially assembly language, which we did before. And so I'll talk about a little bit about these different, this contrast between writing high-level lighting simulation code and making sure that it runs really quickly and fast and efficiently on the hardware that you have. And hardware could be anything. And so we've developed something we call AnyDSL, so I'll introduce you to the compiler, to the language, give you some examples. And we recently started applying that to rendering. So don't expect a full renderer in this talk. We'll show some example, and actually you can go to our booth, the Dreamspace booth, but I have more information about that later. Yes, so let's get started. So I'll talk briefly about VCM, which Christoph just mentioned in his talk briefly, the vertex connection merging with the lighting simulation model, which now it was done by Ilyan Georgiev, one of my PhD students, and made it into a number of commercial renderers, including RenderMan. I'll talk about how we can make real-time rendering possible, the different ways, and in particular I'll talk briefly about the artifact architecture that we did a couple of years ago. And then I introduce to you AnyDSL because it is actually based on the ideas of artifact. And I'll show you how that applies to image processing as an example because it's easy to understand, and then at the end I'll show you how to apply that to RayTracing. Okay, let's start with vertex connection merging. So it's a lighting simulation method. Realizing that, right, we have path tracing, a bidirectional path tracing method on the one hand side, Monte Carlo type rendering methods, and on the other side we have photon mapping. And they use very different mathematical frameworks for computing lighting. And you see that the images that you get out of that are very different actually. So just highlight the center of these images here, and you see that in path tracing there's certain effects like this light going through the semi-transparent vase there. You can't really capture with path tracing. With bidirectional path tracing you can do that, but not for the part that's reflected in the image. And with photon mapping you can do that, but you see that there's a lot more noise around that, and you see this with this inset here much more. That with bidirectional path tracing, that looks pretty good, but in progressive photon mapping, so it's good at one thing. They're pretty much complementary methods in some sense. And so if you actually look at that, right, you can see that there's where one method is good, the other is kind of less good. And so ideally you want to combine these two methods into one. And that's what we call vertex connection merging, or VCM as it's typically called in short. So just to explain that a little bit more in depth, for unidirectional sampling, you simply do path tracing, randomly tracing a ray, hitting something, choosing another direction, tracing a ray, and going on until you hopefully eventually hit the light source or you do some optimization there. That's unidirectional sampling, which is kind of very easy to implement, has lots of benefits, but in many cases that doesn't really, as we saw, it doesn't really give you very good results. And so with vertex connection, you actually start from both sides, tracing rays. And in the most simple case, right, then you just connect vertices between the path that you trace from the camera and path that you trace from the light source. And of course, the path are longer and you trace more of these paths, of course. So that's the connection step. And then in photon mapping, again, it's using a completely different mathematical framework, not Monte Carlo sampling, but density estimation. You start from the light source, tracing photons into the environment wherever they hit the surface. You deposit these photons here. You store that in a photon map. These are the red dots here. And then in a second pass, once you've done that, then you start rendering from the camera, and when you hit the surface, you kind of look for photons in the neighborhood, and you estimate the illumination in that area. So it's a very different approach. But however, you can combine the two. So here's the bidirectional Monte Carlo path tracing. You kind of start tracing. This is the common part between the two methods. And then you kind of tear it apart. And then on the one hand side, you have this what we then call vertex connection, right? You connect the two paths here. And in the other case, you continue tracing from the light source. You hit the surface somewhere, and then we call this merging, right? Which, if you identify in the neighborhood of a vertex, if there are other vertices from the other side, from the camera, from the light source side, then you're kind of identifying those vertices, connecting them directly in that sense, and you do that based on the radius. And actually, you can get an unbiased or actually consistent method by doing progressive rendering and lowering the radius towards 0 in a defined way, but I can't go into detail here. So it's a really nice method, and you can show that this exactly computes what photon mapping would have done, but within a Monte Carlo framework. So it's a really nice way to develop algorithms that combine the two. So this was a major step forward, I believe, for global illumination rendering in general. So in general, the procedure works by, right, you trace the light path, you build some data structures, and then essentially you do path tracing, you connect to light sources, directly connect to the vertices, so the vertex connection part, and then you look in the neighborhood whether there's other nearby things that you've traced in the first one. You combine them all with multiple importance sampling, which was already mentioned, and there's a little bit of math behind that again is in the paper. And then you can reduce this radius, and you keep iterating, and again you have a fully progressive method, which is really nice. So just to give you a couple of nice images here, so this is the scene done in path tracing. You see that there's a lot of noise. By going to bidirectional path tracing, you can eliminate a lot of this noise, but there's still rendering artifact in the mirror in particular. Progressive photon mapping, you get these semi-transparent shadows, right, but you see that there's a lot of more noise now in other parts. And if you combine this with VCM method, that gives you kind of the best of both worlds. And just to go back to path tracing, which is like the preferred method for many people today, still, it makes a huge difference without actually too much impact on rendering time. And this image clearly quite nicely shows, particularly in the red parts, but also in the green parts, where we stochastically combine, using multiple importance sampling, the Monte Carlo, the original Monte Carlo sampling, and then these still now Monte Carlo sampling methods, but they sample essentially the photon mapping aspect of the computation. And then if you let that run a little bit longer than just a minute, then you get nice converged images. I'm always amazed at the rendering times that people cite. I consider an hour really long, and so and we're talking about 70, 80, and more hours here. But the scenes are much more complex, of course. And yes, this has been integrated into RenderMan and a number of other renders as well. So, and actually, that makes me really proud that some of my students have been able to create something that was actually picked up quite quickly. Okay, so, but I was supposed to talk about rendering. And so one of the key things is here, Ilyan, who developed VCM, is the main author in that, actually is also the author of the artifact system for doing fast ray tracing. And I'll talk about that system a little bit later. But if you look at his code, in order to develop VCM, he fall back into a single stupid, non-threaded, single ray tracing code with no SIMD, no nothing, and it takes forever to render an image. So why did he do that? Well, even with Artifact, it's difficult to write an algorithm and get performance out of that, right? You either have to choose a flexible environment for developing the algorithm, but then the result will be slow, or you optimize for performance, but then it's so involved to doing that that you can't really make progress on the algorithmic side. And at the end, what we want and what we need, I believe, is really the combination of these two things. And that's really the motivation for the work that I'll talk about a little bit later. So it's really the combination of optimized implementations and improved algorithms that will bring us closer to real-time global illumination rendering, which is all our goal. The better hardware support, Intel and other companies will hopefully take care of that part. So we don't make much impact here. Yes, and there is an EU project that we started about 1.5 years ago called Dreamspace. And the goal there is really what can we do to reach real-time lighting simulation and rendering for virtual production environments. So that's the other part of the problem, right? We're not just targeting CPUs. There's a lot more stuff out there, in particular if you buy a processor today, right? This is actually a Broadwell die here. You're computing with C++, you're doing your computation over here, and you see that there's many, many more transistors actually on every one of those dies that typically called a GPU, but it's really a parallel processing unit. And no, these are not to scale. This is a Kepler chip. I didn't find a later one. And the upcoming Knight's Landing, which we don't know the number of transistors here. But you see there's many, many more transistors, and you can't use the traditional programming model to do that. You have to go to CUDA and other stuff, OpenCL maybe. And so we can't really, there's lots of transistors on our processors, but it's really hard to take advantage of that in a flexible way and while wanting to achieve high performance. So let's look at what we can do to achieve that. And the most important thing to note is von Neumann is dead in actually two senses. As a person, as well as the von Neumann model of abstracting the hardware, right? That is not possible anymore. You need to be aware of SIMD width, of SIMD instructions. You need to be aware of memory layout, of alignment, because that will make a difference in how you access memory, the memory hierarchy, the caches, and local memories. You need to take that into account, right? Some people believe that, eventually the compiler will do that for us. And there's two main reasons why this will most likely not happen. The first of that is the languages that we're using today, in particular something like C++, but also Java and most of the other languages, they only allow you to express a tiny fraction of what you as a developer actually know about the problem. So the compiler doesn't even know what you want, right? How can it generate optimized code when it doesn't even know what the goal is? And second, even if it would know that, essentially all of the compiler algorithms are NP-hard. And so it has to apply heuristics, and well, sometimes they work, and then you get good results. And in many cases, they don't, in particular when your code gets a little bit more complex and renderers are not trivial code. So then it doesn't work. And so programming is really about abstractions. And if you look at traditional languages, yes, they give you lots of ways to build conceptual abstractions while you're programming, but they come at a cost because the conceptual abstraction in your code are translated into implementation, virtual function calls, and there's something like that. And that kind of makes it hard for the compiler to actually generate good code. And so you have to program in a way that good performance comes out of that. And if you do that, your algorithms don't look like what you started with. And so we wanted to do something about that. So what can you do? Well, what we did and what others did as well is, well, you manually did that. That's what we started with. And right, you see some simple C++ code on the left. And once you're done converting that into SSE code here on the right, you have no idea what that is doing. But it's really fast. Right? Whatever it does it really fast. Well, if you've done it right. And we'll come back to that. And then people started saying, okay, well, we can't do that for everything, so maybe we create optimized libraries. That's, for instance, been done with the Embry team at Intel. They created optimized libraries for CPUs. OpenCV for image processing, it will be our reference system when we talk about image processing in a little time. And so OpenRT and Arauna, actually, by the way, was a really nice renderer, or actually probably still exists, using directly hard-coded SSE rendering at the time. But that obviously doesn't scale. And so a lot of people are now looking at domain-specific languages. So the idea is very simple, and addressing one of the things I just raised is, well, if you can't express your problem, well, maybe you have to invent a new language where you can express to the compiler what you know about the problem. At least you can express it better. The problem is you have to design a language, and you have to design a compiler to go with that. And very few people are actually good language designers. And even less people are good compiler writers. And so that doesn't always work out really well. By the way, rendering shading languages are just a special case of domain-specific languages. So, but people went in that direction. Optics actually has a built-in kind of very specific domain-specific language for the style of ray tracing it does. Halide is another one for image processing. And of course, there's many more examples here. So let me take a detour and talk about Artifact, which we created and published at High Performance Graphics in 2008. So the idea was, well, designing a new language is hard, so what can we do with what we already have? And what we had was C++ and templates. And with templates, you can do template metaprogramming. Actually, templates are a functional language on top of the core of C++. Except with a really weird syntax. And, but it allows you to do things, and that, oh, I should say, this functional language on top of the core of C++ actually is executed in compile time, and so that's where the metaprogramming comes from. And so the idea was that we separate data structures from algorithms so we can change the representation in memory from the way we represent the algorithms. That gives you a lot of freedom here. And we combine them essentially through template metaprogramming and inlining. These algorithms, then we can specialize them for the hardware that we have. We can hierarchically compose them. I'll have a couple of examples in the next following slides. And so then through inlining this template meta program is executed by the compiler at compile time, and it generates compact code that the compiler, there's no function calls in there anymore if you use inlining. And the compiler then hopefully is able to optimize this piece of code. And by 2008, the compiler, C++ compilers, particularly the template aspect of that, were at the point where this actually worked. Earlier compilers were just really bad at optimizing the results of that. And so just to give you an example of, or give you an idea of what an artifact code would look like, is here, right, we define an array packet, which would consist of origin, direction, minimum and maximum distance, for instance. The origin is a vec3f, so it's a vector of 3 floats. An array that, and here you see the template argument. So the size, the number of origins is an argument here to this array packet, or a template argument to that. And then, of course, we have the same number of direction and so on. And you could set size to 1 and you would get a single array. You could set size to 4 or 8 and you would get a packet of 4 and 8. And through something that's called template specialization, you could provide an implementation for the case 4 and actually implement it with these ugly SSE instructions that you showed, that I showed on a previous slide. So you only had to kind of implement at the lowest level these vec3f operations, addition of vectors and so on in SSE, and then all of the higher level stuff was essentially generated automatically by the compiler. And yes, we could also then, if you wanted a 64 packet, then this was the compiler would automatically know that, well, it has to break it down into n numbers of packets of 4 arrays because it had a specialization for that. And what was really nice is you could actually have packets of, I don't know, 4 rays, single rays, 64 rays. All of this could exist in the renderer at the same time. And in different parts of your code, you could use different versions of that, and they were all automatically generated. And then you can have something like, actually C++ at some point suggested to have something like concepts, which is essentially interfaces on template classes. It was suggested but never made it into the standard, but we kind of used it by convention. So here you see a template class for KD tree, right, with methods, so to say, for creating inner node, leaf nodes, roots, getting left, right children, getting the split plane, and so on. And with that way, you could actually nicely separate the way how you laid out your memory data structures, and then you can have algorithms for building KD trees that take advantage of that. And so you could separate the representation from the algorithms working on the representation. And since this was all inlined, the compiler kind of integrated the code. So you had a difference between conceptually you had separate implementations, but the compiler integrated all of that together. And you could actually do things like create bounding volume hierarchies that contain KD trees that were built on top of triangles. And you could have an intersector, a corresponding intersector, right? You could specify that is the data structure. And then you could specify the algorithms working on them, like an intersector that would traverse that KD tree, or the different spatial acceleration structures here. And again, this would be combined through inlining, and the compiler would generate the code, the resulting combined code at compile time, and then optimize that, and that's where we get a lot of the performance. And so the nice thing about that is at the high level, so in your main program, you could very easily configure very different ray tracers. Here you say, okay, I have a pinhole camera, maybe an OpenGL frame buffer. Let's say my scene consists only of triangles. I have a bounding volume hierarchy over triangles. I have a simple builder here, which I give all the scene triangles. It builds me that. I have an intersector which uses for the triangles, here for the triangles in the BVH, it uses a Plicker triangle intersector. And then you have a ray tracing renderer where how you sample and how you do the integration. And then you simply said, okay, go ahead, render. And by the way, render with packets of 64 rays. And from this simple code, it would grab lots of pieces of text and would combine at compile time a highly optimized version of the RayTracer. And if you write this here, okay, I have a basic scene over points. I use a different spatial acceleration structure for points because they don't really have an extend. Having a corresponding builder, a different intersector here, and you can define another renderer. And you can have actually both of them in the same program if you really wanted to. And so for using the program, Artifact was actually, for building ray tracers at this level, was extremely efficient and very nice to use. And actually, if you look at the performance, it was actually really good. So here's for KD trees in the top, several different scenes here. Oh, by the way, this is surface rendering here. This is volume rendering in the same framework, and this is point rendering in that framework. So this is only for surface rendering here. And you see that Artifact even outperformed our OpenRT and the Manta system, or here with BVH spatial index structures, were roughly as fast as Arauna, which was a full ray tracer for gaming environments. A very, very low level optimized for the entire ray tracer. So that's pretty good, right? So here we have a system that gives us performance that was over the bench of different scenes and test environments, was within 10% of the performance of highly hand-optimized code. That's great, and right, you could program at a fairly high level, as I just showed you. So high-level programming was very good too, right? So as I showed you, you can compose things. But what I did not tell you, if you did any error there, you got a 5-page error message, and there was simply no way of figuring out what was actually going wrong. Or well, it was possible, but it was very tedious. Compilers were not very good at the time to report errors in template code. But if you actually had to implement an algorithm within the ray tracer, say you wanted a new intersector or a new traversal algorithm, that turned out to be really, really hard because you had to write this in this template language, and template language doesn't even look like a programming language. And also, like, virtual function, which is sometimes you need, doesn't really play well with metaprogramming, template metaprogramming. And if you even think about maintenance, that's essentially a no-go. Right? This code is, I always call it write-only code. Right? There's just, if you look at the code what you wrote today, 2 weeks later, it's really hard to figure out what you wrote and what it does. So it showed that in principle this approach is possible, right? Except the tools that we have are not the right tools. And that, funny enough, around that time, Sebastian Hack joined our faculty. He is a really great compiler professor. And so we did a lot of different things, but the key outcome of that collaboration is AnyDSL. And so I'll walk you briefly through AnyDSL. And actually, I'll use image processing because it's just simpler. And then I'll show you kind of what AnyDSL does. And then I'll show you how we apply this now to RayTracing. OK, here's the vision of AnyDSL. OK, we want to provide a single high-level textbook-style representation of algorithms so that we want you to just write textbook code. OK, and we also want to provide you a mechanism for describing how to map some of these code abstraction that you use in the code to hardware architectures. So it should be very simple for you or for someone who knows the hardware well, let's say more hardware engineer, hardware-focused software developer, to write, maybe do that mapping. How would you do the iteration over pixels or over arrays on a specific hardware architecture? And then we want to obtain optimal performance on each and every hardware platform from GPUs to CPUs. That's right. Most people would say that's you might have visions, but that's a good way to, maybe you should go to a doctor. Maybe that's just completely wrong. Well, actually, it's not. Here's the results of, so this is stencil code, and we compare against OpenCV, which is like the computer vision and image processing library out there. It's been heavily hand optimized by each of the hardware vendors. And on NVIDIA GPUs, we even beat the hand optimized code by about 10%. For AMD GPUs, we beat the hand optimized code by 20%. On embedded Intel GPUs, we even beat it by 25%. On CPUs, we beat the Intel code by even 35%. Right? That should never be possible, by the way, right? Because whatever code we generate, you could claim that's my hand-optimized code. So at best, we could achieve 100%. We actually get better results, and I'll explain you in a second why. So what are the goals of AnyDSL in more specific? The main goal is give control back to programmers. Right now, you have some arbitrary code sitting in the compiler, looking at your code when you start the compiler, and making decisions of what it thinks the best way to map this special construct to whatever hardware the compiler is compiling for. And you pretty much get not really a lot of choice there or could tell the compiler what to do. We want to give you full control over that mapping. In many cases, it's very easy to write that, and you can actually maintain this and reuse that. It's very easy. Right, you could just have this as libraries, prepackaged, right? It's packaged right now already because it's part of the compiler. You just don't know it. It's been integrated there. We give you the way to use different libraries of mappings, for instance. It should be applicable for any domain. So we don't want a specific domain-specific language that only works for ray tracing or only works for, I don't know, point processing or only works for shading. We want a single language that allows you to define the specific domains you want to abstract for. We want to allow you to define entire hierarchies of abstraction. That's really what programming is all about. And these abstractions, actually, the way we present them to you is just function interfaces. Very, very simple things. Things that every developer writes down every day. And the transformation or the mapping of these abstractions to hardware or to some lower level abstraction, remember you can do an entire hierarchy of those, actually will be just code. You just implement that function in terms of either hardware intrinsics or whatever hardware interface you have, or in terms of lower level abstractions, function calls. That sounds like we haven't really gained much, but the key part is that we allow you, and I'll show you how that works, we allow you to specify that you want specialized versions of that, and that eliminates essentially all of the overhead across all of these levels of abstractions. And the really nice thing is you have these hierarchies of abstraction, and at each level you might feed more details about the code that you're writing. I'll come back to that. And the compiler in the specialization step will gather all of that information and generate a highly optimized version of that. Okay, here's the basic mechanism that we're using, and I'll use a very simple example. So on the right you see, on the left you see a dot product in our language. So we actually, our language, we call this Impala. This is our research language. It's actually based on Rust, which is a really, really nice language being developed by Mozilla. It's actually, in terms of features, pretty much 80% the same as Swift from Apple, which is gaining a lot of attention now. And so here's a dot product. So the length of the vectors, 2 vectors, arrays of floats. You initialize to 0. You iterate over the number of dimensions. You multiply the element-wise, sum this up, and return the sum. Simple dot product. So here's the key. You can compute a dot product from 2 vectors, and maybe at this point you know that the vector length is 3. And by simply putting this @ sign in front of it, you're telling our compiler, I know you can specialize this code. And this triggers an absolutely aggressive specialization technique. What the compiler actually does at this point, when it compiles this instruction here, it interprets this function, it essentially executes this function at compile time, and it executes everything that it knows at this point, right? So if you add 2 numbers and it happens to know those 2 numbers, it will give the result, right? It will do the addition for you at compile time. And so in this case, we know the loop range, and so what will happen is essentially the code will just unroll the loop here, and you just get 3 multiply adds as a result of that. Actually, if we would know one of the vectors at the point, there would be constants here, and if we would know both vectors, we would return 42 or whatever the result is. And there wouldn't be any code executed at runtime. Okay, all of this is actually integrated in our AnyDSL framework. At the lowest level, we're using LLVM to generate code. Why reinventing the wheel? On top of that, we have a unified program representation that uses something called CDR representation, continuation passing, CPS, continuation passing style. It's actually not a new technique, but it's very, very flexible to represent programs at a very high level. Actually, functions are still there, control structures are still there, types are still there. So as a lot of things that are in normal compilers in LLVM, you go down to essentially instruction level representation, so you lose a lot of the information. This is still there, and then our Thorin compiler framework, that's the internal compiler stuff that operates on this representation and can perform a lot of high-level operations on that. The key point is that everything you ever write in AnyDSL is transformed into this same representation here right away. So if you define a computer vision DSL or physics DSL or RayTracing DSL, right, this is immediately converted, right, and you can layer DSLs on top of each other. All of them is directly converted into this common representation. The compiler doesn't even know that this came from a RayTracing DSL, and that may come from, I don't know, parallelization DSL. And so it can combine all these different DSLs together. And you, as a developer, you get to write all of these things. And yes, there could be 10 different RayTracing DSLs, 10 different ways of building abstractions for RayTracing. And the idea is that over time we will converge. Different people will suggest different ways of defining RayTracing, defining abstractions for RayTracing. And over time we'll converge to what is the best way of doing this. And we're starting along this direction now. So again, I will show you examples in image processing because it's very easy to show things. It's a little bit more complex in ray tracing. So here is your textbook style image filter. Right? You're getting a coordinate, you're getting an image, you're getting a filter, which is just an array of floats. Right? You iterate over, right, in 2D over your filter size. You grab the neighboring pixels, you multiply that by the filter, and you sum this all up. I mean, this is literally textbook code, right? Nothing really special, just translated into our language here. Okay, so that's a generic filter. So maybe we want to do a Gaussian filter, right? In this case, you can actually use what we just did. So you want to do a Gaussian blur. Oh, so you allocate a return image here, you define what your filter should be, and then you say, okay, I want to iterate over all of my pixels in the image in X and Y. I'll come to that, what this is. And then for every pixel, right, I want to apply this convolution operator that I just defined and write the result into my output image. Very, very simple. So nothing, right, everyone could write that. So the trick is, there's a little bit of tricks here. The first thing is, look at this line here. So this for loop actually is nothing else than syntactic sugar for an iterate function that takes the image and it takes a lambda function, which is the body. The body of the lambda function is the body of the for loop, and the iteration variables are the variables of the lambda function. It's just a little bit, so you get to write this one, but you get to implement this version here. Okay, so this will compute our Gaussian blur. And by the way, right, we know this filter now. We know the size, we know its content. Right, so the next thing we will do to make things faster is we'll put this @ sign in front of this. So essentially this, at this point, will unroll this for loop in the code. And again, we know the filter, so actually we'll put the filter coefficients in there. Actually, if there are zeros in here, it would not do it would not fetch the data, it would not do the multiply, because the compiler can figure that out at compile time. That is not necessary. But the key thing now is this iterate, because that is where a lot of the mapping to hardware actually happens. So here's the very, oops, too fast. So here's the trivial implementation of iterate in a sequential way on a CPU, let's say. You're getting the image, you're getting this lambda function that implements what you should do per pixel, and you sequentially iterate over all the pixels, and you call this lambda function. Right? The point is, when we later specialize this, right, the lambda function will actually, this body function will actually be, right, inlined here at this point through this interpretation step, and this will be reasonably fast, right? But you still have this sequential for loop here. So if you want to do vectorization, so if you want to do SIMD, in the past you had to implement all of the ugly SSE or AVX intrinsics. In this case, we actually implemented a vectorized function for you. So let's say here we iterate sequentially over the rows of the image, and we vectorize over within a row, and we simply, right, you can simply tell the compiler, right, this is my vector length, and please vectorize the resulting code here in the parentheses. This is just simply to know where in your length vector you are, and then for wherever you are, you're iterating here the body function. And you get a, right, without doing much work, you're getting a vectorized SSE or AVX implementation of that. Oh, you wanted to target a GPU? Well, not really difficult. You simply write another implementation of this iterated loop. It takes the same thing. Here we defined the grid and block structure, right? In this case, we decided, okay, 32 by 4 is good for this hardware. Actually, we specified it here at constants, but you can actually compute that at compile time or even at runtime at some point. You don't have to specify this as constants here. And then again, we give you, because we know our backends, we give you a way of generating CUDA code, or this NVVM low-level interface to the CUDA driver. This looks exactly like the normal CUDA introduction code, right? You simply get your index from the grid index, and again, then you call whatever has to be done per pixel. So that should be familiar. Whoever did CUDA, you just write this. And right, I left out a lot of details here because of time. But the really nice thing is you can now try, with very, very little code, different optimization strategies. So what you see here is, first of all, a matrix and with the performance numbers, and we have different optimizations. So here, this is the straightforward Gaussian things, which we didn't really look here. We did the simple one. Here we actually specified the stencil, so we optimized for knowing the stencil. Here we also implemented boundary handling through an optimization that I don't have time to go into. And here we also included local memory, or scratchpad memory, as it's sometimes called. And we also went through the NVVM layer, or we used OpenCL, and we used a single one where every GPU thread just computes a single pixel, or here an unrolled version where every GPU thread actually executes for multiple pixels. And this is all, essentially you can write this code within a day or a couple of hours. And you can try out all the different options and find what is the best performing way. And actually for NVVM, it turned out that, we should say, the OpenCV is the reference implementation from OpenCV, the performance on the same hardware. That was, again, this was hand optimized by, I believe, NVIDIA GPU optimization people. And it turned out that their optimization strategy is actually the one that's also the fastest for us, except that we're 10% faster than the code that they had. Right? Remember, we're 10% faster. They implemented probably weeks of optimization there. It's much more elaborate code, while we just wrote the same high-level code and specified how to map it onto a GPU. For OpenCL, it turns out that's not well implemented on NVIDIA, so it's much slower. And it actually turns out that there is an OpenCL implementation in OpenCV, and it actually uses the wrong strategy. This one is actually faster. But it's much slower than the CUDA version. So let's look at AMD GPUs. That's an Radeon R9 2900. And again, we can go through the low-level spur interface or through OpenCL. In this case, it actually turns out they both have the same performance. Again, we can try different versions, simple and unrolled. And it turns out that the unrolled version is actually faster than what they implement in OpenCV, and overall we're 20% faster. Well, it turns out that our implementation of their strategy is actually faster than their implementation, but it turns out another strategy is even faster than that. And this is where we get 20% performance over their implementation. And so on Intel Haswell, actually go to the GPU, oops, sorry. Actually, I think I messed up something here with the numbers. Yeah, actually, this is, let's do this one first, but the numbers are wrong. Sorry for that. So this is Intel Haswell, the built-in GPU on an Intel processor. And again, we can try different methods and compare this with what they implemented in OpenCV. And we're 25% faster in this case. I think I mixed this up. And there is a CPU version with a sequential code or AVX implementation. And again, we get about 35, actually, not 25. I mixed them up. Now here it's interesting. Again, you saw almost all of the code on my slides. So there's some, the other mappings here are a little bit more complex, but it's never more than like 30 lines of code. The implementation in OpenCV is 1,500 lines of SSE code. And that's also why we're faster, because it takes a lot of time to write this, and you don't want to write different versions of that for different strategies. So you try one, maybe two, maybe three, and then you stop. And, well, maybe you didn't find the best one in the process. And in our code, you just change a couple of lines, you recompile, and you see how much faster you are. Okay, the really nice thing about this whole approach is that you can separate the concern, right? So maybe you have a DSL developer who says, oh, I know how to do image processing, what operators to implement, how to do that. But he doesn't necessarily have to know how to map it to a certain hardware. So maybe you have a machine expert, maybe he's coming from NVIDIA, from Intel or whoever, and they know, oh, so this guy here creates abstractions like this iterate loop that I showed you. And this guy here says, okay, I know how to map that to hardware, to different hardware. And the user on top doesn't really care about any of that. He just gets this Gaussian blur function at the high level. He just applies it to an image. And the really nice thing is that the AnyDSL compiler, by simply putting this @ sign in front of a function call, right, it takes all of the information that was provided here at the top. Right here we have the textbook implementation. Here at this point we did know the size of the filter and the coefficients. Here I left out the slides for boundary handling. That was maybe known at a slightly lower level. At this point we know what are the constants here. Maybe we know cache size. And so at different points, at different abstraction level, you have different information. And when you specialize the code, that gets all integrated, and the resulting code is highly optimized. So finally, let's talk about how we apply that to ray tracing. And this is still ongoing, so I can only show you preliminary results. So again, within the Dreamspace project, which is an EU project, as I mentioned, the goal is to develop these proper abstractions, and we don't really know what they are, right? There hasn't been much code yet that targets both GPUs and CPUs. So what are the right abstractions here? This is not entirely clear at this point. In particular, it's not clear which of these abstractions lend themselves to the best possible mappings on the different hardware architectures. And there's new hardware coming, like the Intel Knights Landing CPU, which is really interesting, particularly for rendering, I believe. And we don't really know how to address that. So it gives you flexibility, the algorithmic flexibility, and the cross-platform optimization by writing the general applications and then specifying separately, as I showed you, the mapping to hardware. And then what we target is really at least get close to the performance of Embry or optics on the GPU. And the question of the project really is, can we render these VCM methods, this vertex connection and merging, can we render them in real time and do virtual productions with full lighting? Maybe we can't do that on a single core. Maybe we need a couple of machines for that. But the question is, can we do that, and how much can we scale this, and how efficient can we get this so that we can lower the number of hardware resources that we need to actually implement that? So a very simple RayTracer, and actually this brings us back to Artifact, is pretty much this. So we have a RayTracing method. You give it a function to generate rays. You give it a function, a higher order function here as an argument for how to intersect, and a function to compute material. So this is obviously very simple RayTracer. It only has a single material model, only a single intersect function, but that gives you already an optimized RayTracer, and it's very much similar to what I showed you before. Of course, you want to make this a little bit more complex and have programmable materials. I'll talk about this in a second. And again, then we can have these mappings, right? And so again, we can have an iterate function. And this was like the first code that we started with, right? So here we can say, okay, I want to multi-thread over the scan lines, and within the scan lines, I want to vectorize here. These are actually implemented using, so this is essentially a parallelization DSL that was implemented using thread building blocks from Intel. Vectorize, as I said, is built in. It takes our whole function vectorizer. And on the GPU, we just map all of this to NVVM. And again, you might want to compute the best optimal or the best grid size and things like that here. So it's a simplified version, of course. This was our very first images, or early images, I should say, maybe not the first ones. But we could already get like 20 frames per second. This is using instancing with fairly many triangles here. But a very simple RayTracer. This is actually the scene that you will see at the Dreamspace booth. So we have shadows. Actually, these structures on the floor here is actually shadows from some structure in the roof here. There were some issues with materials conversion. As with all the demos, things come together much later than you thought, and there's some last-minute glitches, so not everything is perfect here. But it's also halftime of the project, and it's very unusual that you have a full integration of all of the tools of the project at this point already. But yeah, please come visit us at the Dreamspace booth, and we can talk about a lot of the details here. So a little bit more information here. Initially, of this year and a half, we focused a lot on the compiler itself. It's not perfect yet, but it can actually deal with this widget style RayTracer. So the generic RayTracing code is about 4,000 lines, which is not really a lot. It runs on the GPU as well as on the CPU. We're currently, we can't do everything at the same time. We're mostly focusing on the optimization on the CPU side. Right now, I just got a new PhD student who is now looking at GPUs. And all of this has been integrated in Katana, not because we want to make it a product, but simply because the Foundry is one of the project partners, and we wanted to show an integrated version here at FMX. Initially, we were not looking at performance, but really at what are the right abstractions. Now, in the recent, actually, couple of months, we only started looking at performance. And what's actually interesting, so we started with the intersection computation. Our current intersection computation is within 30% of the Embry time for the same thing on the same hardware. And that is actually due to limitations. We know limitations that are in the current compiler. And so we can definitely get this much closer. We have initial numbers for other parts of the RayTracer, but they haven't really been optimized yet, so I can't really talk about this in much detail at this point. But that is what we will be doing over the next couple of weeks and couple of months. So where do we want to go with this? The general architecture that we're working out at the moment, and this is a snapshot of what we currently believe to be the right way of doing things, is really a queue-based system where you have different modules for generating rays for intersection computation. Once we have intersection, you might apply some rendering logic of how to do the integration. Then the integration, so the integration is actually happening here, but it uses the materials. You might have many different materials. And then you might do some reordering and then keep looping over rays here. And the key thing really in our architectures are these queues here, or some people call them pools of rays, because you probably want different sizes of computational units. So maybe you want, depending for first generations, maybe you want to generate fairly large packets of rays here, at least in the top of the tree. Maybe when you come from shading, maybe you want to do shading in much smaller packets of rays. And so these queues allows us to kind of buffer things in between, also allow us to do much broader, particularly for GPUs, you want to have much broader executions of kernels, for instance. It also allows us to distribute things across machines eventually. That's not really a goal right now, but that might be a direction we want to be going. The other point is that, yes, we can do that specialization that I showed to you, but you probably don't want to specialize the entire RayTracer. Right? You don't want to put an @ sign of the main on top of the main function, right? You probably could. Your compile times would probably be fairly long. It would probably work. Well, maybe not with the current compiler, but hopefully it should work in principle. So there's some known limitations right now. But the key thing is you want to localize this optimization. You have to, at some point, you have to define what you want to optimize over. And so our current ideas are around optimizing each of these parts. So the ray-scene intersection part, the integration part, and the materials. There's some discussion whether we should bring things closer together between these two. And as I said, the queues is a really nice mechanism to kind of define the interface and decouple the optimizations. So one of my last slides. So the current work that we're doing, what we're focusing on, is really working more on these abstraction, really finding out what are the best abstractions, also that work well on the GPU as well on the CPU. By the way, I should say that doesn't mean that we'll be executing exactly the same algorithm. Right? So maybe building a BVH we will be using very different algorithms on the GPU than on the CPU. But the abstraction should be the same, right? Then you can use to decide that you want to use a different method, a different implementation of building a KD tree, for instance, on the GPU than anywhere else. But it shouldn't change the core code of your RayTracer anymore. It essentially just changes how you configure the core code and the implementation on top of that. Of course, that's the main focus right now is create these optimized mappings, and we really want to get close, at least get close to Embry and optics. Optics on the GPU, Embry on the CPU, and Knight's Landing and things like that. Then we want to do the parallelization distribution because we know we need to scale. And the streaming computation through queues seems to be a very good way to approach that. And yes, of course, eventually we want to go back to do this in real time. So path tracing is certainly the first step, but we have a student now that is implementing VCM right now. And of course, there's bugs in the compiler. It's not something that we can make available yet because there's just, you need to know what you're doing at this point. But the entire goal is to actually make that available, all of that available as open source. So to conclude, we have this AnyDSL framework that gives you this high-level, higher-order functional representation. We have this novel concept of allowing you within that language to define abstraction as well as define how to map them to either lower-level abstractions or to hardware. The developer is in full control and can use tools like partial evaluation, vectorization, and target code generation, things that developers didn't have access to in the past. I showed you image processing. We're doing much more in this area as well, going a little bit towards computer vision algorithms as well, and then we're doing this ray tracing work that I just showed you. And yes, this is pretty much still work in progress. In particular, the RayTracer was only started it depends on how you look at that, 2, 3, 4 months ago maybe. So there's still a lot of stuff that we need to be doing. We're certainly far away from a Pixar-style renderer with everything integrated. But on the other hand, I think we have a number of tools that we created here that will allow us to achieve these results well, we probably will never write a full RayTracer like a Pixar RayTracer or any of the others that we heard about today. But at least it should give tools to make that much easier and address different hardware architectures in the process without too much additional cost. With that, thank you very much. And if there's any questions, I'm happy to answer them. Here is the address of our booth. Feel free to come there tomorrow or whenever, and we can tell you much more details if you're interested. Thank you very much. Are there questions? I don't really see much from here, but yes, there is one at the back. Can you wait a second? There is a microphone coming.
Other than rendering and perhaps ray tracing, have you ever tried to apply this to other very computational, extensive, and expensive fields?
We currently have a multi-grid solver that we've implemented with that. We have talked to the database guys, but we haven't really started working on this. But they are very interested because they have exactly the same issue, that the core algorithm that come out of the query optimizer, they also want to map that efficiently on hardware, and currently they essentially just do it for CPUs, even though they know that if they do some of the sorting and some of the other algorithm, they could very, very easily map that to GPUs and get a huge speed up. But just from a software engineering point of view, it's overkill to even try that. And so we've talked to them. We don't currently have a student for doing this. Yes, and then we're looking at, actually I have a multi-agent group, so agent-based programming is something we probably want to look at as well. But yes, there is no limitation because you can just define your own abstractions, right? And so if you want to apply that to, I don't know, something else, once we can give the compiler out, you should be free to just do that.
Okay.
Other questions?
One last question.
When do you think you could release the compiler?
Within this year, certainly. Yeah, I mean it's a research in progress, and at this point, if we would release it, there would be just too many questions. We would be overwhelmed. You kind of have to know what you're doing right now.
Okay.
I think there was another question. I think we can take maybe one. Yeah. So.
Hello. One question about vertex connection merging. Which renderers are using it now? I know Renderman, of course, Corona Render, and V-Ray.
V-Ray. I think there was at least another one. I forgot which one, actually.
Thank you.
I mean, that's those that we know about. I mean, there might be others. Yes, so with that, thank you very much for listening. And, well, again, see you at the booth.
Thank you.